privileged to have two gentlemen from Sika with us. Sergej Harder, he's a CA engineer specializing in adhesives, and he's joining us from Hamburg, Germany. And we've got Curtis Mankewich, he's a technical sales rep. It says here Edmonton. I was going to make a joke about the Oilers and the Jets, but unfortunately fortunately for us, he is in Winnipeg. And I'm hoping he's a Jets fan. I don't know, I guess we'll find out. But anyway, what we're going to do is we're going to pass this over to Sergej and Curtis, and they're going to present. And then when they're done, we'll open it up for Q&A. Please feel free to use the Q&A feature within Teams, and we'll be happy to answer your questions. And once that's done, we'll wrap it up. So what I'd like to do is I'd like to introduce Curtis Mankewich. He's a technical sales rep with Sika Canada, and his territory is Manitoba and Saskatchewan. And he works in industries, transportation, aerospace, defense, agriculture, and electronics. And he's the tech rep and specializes in the use of adhesives in production. He's a grad from the Red River College, and he's got a background in transportation with OEM and aftermarket parts manufacturing. And Sergej is joining us, as I said, from Hanover, Germany, and he supports customers from different industries with bonded joint design and verification. He's got a background in material science and experience in research as well as structural design. And he's the interface between engineers and Sika. So with that, I leave it to you gentlemen to carry on and present. Thanks so much for doing this.
Excellent. Thanks for the introduction there, Ron, and thanks for having us today. As mentioned, I'm Curtis with Sika Canada and based here in Winnipeg, and just going to go over a few things in regards to Sika in case you don't know what we do, and then I'll let Sergej take over in regards to our fully bonded cab design. So some of the things, just like with our cab design, we work with design engineers, production managers, quality managers to offer cost savings, highest quality possible, and increased productivity. Some of the different methods that are used in joining materials, whether it's composites, metals, anything there is screwing, welding, riveting, rigid bonding, and elastic bonding. And those are the two areas Sika focuses on. And then these are some of the areas that are to be considered when we're looking at making a change from those methods over to adhesives. So when replacing welds, some of the things to keep in mind is adhesives are more durable than welds, increased productivity, and also a significant cost reduction. It's less hazardous than welding fumes, and then also to Ron's summit there that he's hosting, adhesives do emit far lower CO2 levels, so something to keep in mind as you guys are looking forward to that as well. And again, here's just a few more things to be considered when you are looking at adhesives, whether it's thermal expansion, dissimilar materials, the methods that are going to be used, order of assembly, the volume, durability, and just all the different requirements before we can do an adhesive selection. And then some of the products that Sika does have, we have single component and boosted Sika Flex, which is single component polyurethanes, as well as boosted to accelerate the process. They offer speed, strength, and often less surface preparation. We have our Sika Force, which is a two-component structural polyurethane. We have Sika Fast, which is again a two-component acrylate. And we also have Sika Power, which contains both heat cure as well as two-component cure room temperature materials. And then just to kind of do an overview of what Sika again does offer, we have bonding solutions. We have heat and room temperature curing two-component cures and single-component cures, as well as sealing, which offers again with heat curing and room temperature curing as well. So in that, I will leave it over to Sergej to talk about the fully bonded cab, which is why you're all here.
Okay, thank you, Curtis. So before I jump into the cab, I would like to show just a very brief outline of the basics of the adhesive bonding concepts to consider when designing with adhesive bonds. So just very briefly, maybe for some of you it's obvious, but if you're bonding with adhesives, you're putting a polymer inside your construction. So normally you will bond maybe two metal substrates together. And if you just use the cross-section of your metal substrates, the weakest link in that part will obviously the adhesive, because the polymer in almost all cases has a lower strength than a metal. So for example, we have here some kind of a structural adhesives with 25 megapascal. And if you have a substrate with 200 megapascal and you just use the same cross-section to connect both parts, the adhesive will be the limiting part. So here, just as an example, you will be able to transfer 12 kilonewtons through the substrates. And if you only have the adhesive in between using the same cross-section, it will only be 1.5 kilonewtons. So this will be the limiting factor. So in order to make adhesive joints work, you have to create some of the surface that you will need for the adhesive to act. And that you can see on the right part, mainly used design for connecting parts with an adhesive is the so-called overlap joint. And in that regard, you have still the same substrates, but in that design, you created the surface, which is now the 25 millimeters overlap. And using the 25 millimeters width that you have previously, you now created a much larger surface for the adhesive to act. And now you can transfer much more loads through this design. In that case, roughly estimated 18.75 kilonewtons. And in that design, again, the adherent would be the limiting factor rather than this joint connection. So obviously in a one-to-one comparison, if you just take a weight approach, you could say the welded design, for example, will be superior in terms of static peak loads. And in order to make the adhesive joint work, you have to create the surface, but then it can also, if you have a sufficient surface, it can outperform the weld. Now, a second part to consider when modeling with adhesive bonds is the stresses that you have acting in the adhesive bond. So with this overlap design, you have the shear stress inside your bond, which is okay for adhesives. Just one thing to consider here is that you, most of the time, the nominal stress that you have, for example, or the nominal strength that you get, for example, for the shear labs test, does not consider the stress peaks at the edges. So in reality, which even in these test results, you will see much higher stresses in the adhesive, and you cannot just consider it to be a homogeneous distribution of the stresses. Compression is quite okay for an adhesive bond to take. So this is mostly not a big problem, but it's also not very often in the design. Tension in the case that it's that it acts centrically here on this adherent is also not a big problem. Then it's also mostly quite homogeneously distributed. What you have to prevent in most of the, or try to prevent in your designs, is this cleavage and peel forces. So for cleavage, we mean here an off-centric force acting on the adhesive with a quite stiff adherent. There you have also a non-homogeneous stress distribution, mostly acting on this part of the adhesive. And even worse, if you have a less stiffer adherent, you have then peel forces, and then even a worse situation for the adhesive, because of course you created the surface for the adhesive to act, and now if you have an off-centering, very locally acting force, you take away this advantage or this acting surface for the adhesive, and now you reduce your load-bearing capacity of the joint. Another part where we often get questions, so now I see this characteristic shear strength for my adhesive. Can I just use this strength for my design? And oftentimes it depends also, what will be your temperature that you will see in your application, and you will have to consider the reduction factors for that. So for example, most of the adhesives will lose some of the strength with higher temperatures, but also gain some strength if you have lower temperatures than room temperature, for example. And this you will need to consider with these reduction factors. Also, thickness tolerances can play a role, and also if you have fatigue clothes and so on. And also considering the safety aspect of your application, you will also maybe need to introduce some design safety factor. For a lot of these adhesives that we use, we have the so-called additional product information. So for example, also the adhesive that I will show you for this cap concept, we have this short API where we gathered a lot of testing data, also having artificial aging conditions, where we can show, okay, after a certain aging, this will be the reference strength that you will still have. So we have quite some substantial data for this to check, and also maybe derive these reduction factors for your design. Now, what is the goal of our presentation? We do not want to substitute every connection now with adhesive joints, but it's rather, I think, an important point to have another tool in your toolbox. So maybe currently you mainly use spot welding or welding, being it manual or robotic, and also maybe mechanical fasteners. And I think it's also worth to consider adhesive joining in some aspects of your design. It can be, for example, also hybrid joining, where you have on some distances some spot welds, and then an adhesive bond, which gives you the opportunity to transfer loads through the whole, through your whole adherence, and also have the fixation at the spot welds, which can also be used, for example, if you want to have a fixed connection during the curing of your adhesive. Or of course, just simple adhesive bonding as a permanent connection. I also know from my experience that during the educational part as an engineer, adhesive bonding only plays a very small role, I would say, in general. So this is also where we see our part to also maybe educate engineers and to show them the possibilities. And to show them the advantages of this joining method. Now, where can we support customers? So as I said, we have this quite very comprehensive material data to use for the design, but also we support and to choose what parameters to use for your FE analysis. And we actively work with customers in the projects where we exchange data and also review their designs, and also maybe provide them with methods how to approach or how to validate an adhesive bond. I think that's also quite often the question. Now I see the stresses, for example, in my FE simulation. How do I assess them and predict if my design will fail? And this is also something where we support our customers in. Now, during a project where you would, for example, develop a adhesively bonded solution, my support is always quite early in the stage. So even when you have your preliminary or first designs, I often come as a support and provide you, as I said, with methods, or maybe also to review a design. But we also have dedicated persons in the company where also at later stages of the project they support, maybe also in the implementation of any application devices. So we have quite, I think, a lot of experts in different stages of the project to support you. So with that, I come probably to the most interesting part of the presentation. This is the Advante concept, where we developed this adhesively bonded cap structure. We did it in a project together with the Applied University of Osnabrück, and there the Lightweight Institute is quite well connected to the farming machinery, which is actually also quite close to Osnabrück. So this Damme company that you mentioned, Ron, this is maybe 30 minutes from Osnabrück, so they are very close there, and they know about the specific details of these designs and the specifications and the requirements of this industry. So together with them, we developed this project. And for us, it was also a possibility to, at first, obviously show the potential of the adhesive bonds, but also to have something which is our knowledge, which we can also show to customers. So obviously, the projects that we develop together with customers are most of the times confidential. We cannot show anything, and in that case, we have something to show to the customers which are maybe not very familiar with adhesive bonding. Okay, we have developed a solution here, and we can be very open with the data we have. So you probably already also got the QR code where we have the documentation for this project, and we quite openly show our thoughts behind this, our calculations behind this, and also provide you with a CAD data, for example, to maybe try out yourself and test your approaches and very have in-depth information for this project. So how does it look? So this is the Advante cap concept. So quite straightforward. You have this cap which is connected by these nodes, the yellow parts here, and in between you have these hollow tube structures. And you can imagine it being, for example, you have your top roof and your bottom construction, and you connect them by these vertical pillars, and it's a quite flexible structure, so you're open whether you do the joining before or after the paint job. Since the adhesive bonding application is a quite clean process, you're very much open to when you do it. A very big part, I'll show it in a second again, is this node design that we use here in order to connect these continuous structure or these tubes together. And here in this part, you will see you have the adhesive acting. So we will zoom in here again. And the red part, you can imagine being the adhesive introduced into this section here in order to bond these nodes together with this square hollow section. Now, again, our main goal was to show at first the feasibility of this bonded solution, but a main driving factor is to kind of also show the benefit of it, is to show we have the lower manufacturing costs, and that's what we think we can achieve with this method by reducing the mounting time quite significantly. In terms of mechanical properties, we also can reduce the influences of the thermal joining in these edges here, which can also be a benefit, especially in the durability load case. And I think also, which could be a big influencing or advantage of this concept, is the modular design, which I showed previously. So you can basically pre-manufacture some components and then later join them together. In the end, we have achieved a fully bonded structure frame. We have the following dimensions for this cap. We took an example of a real tractor and basically reverse engineered or tried to build a fully bonded frame structure for this tractor here. So it has quite some realistic dimensions. And we also, I will show in a second, showed that it's ROPS and FOPS approved. So for our dimensioning criteria, as I said, we took this tractor and we knew the mass by the specifications, which was 8.5 tons in that case. And from that, the standards can derive the certain load cases for the rollover protective structure and for the falling object protective structure. And we took this as an input for a topology optimization, mainly to get the geometry of our nodes, but also to see a rough dimension of our structure here. And this is where we started with. So from the node design or from the topology design, you can also quite see how the node design derived with these rounded edges. And you will see this in this slide in more detail. So this is how the node looks like. And this is kind of optimized for adhesive bonding. It's a hollow structure inside, so it's also possible to pass cables through these nodes. Then you have this recess for the centering of the square hollow structure that you put on top of these nodes. And it automatically also centers this square hollow structure. On top, you have this joining channel where you apply the adhesive. This can be manually pumpable, for example, also for a robotic application. And then on the bottom side, I will show in a second, you have, for visual confirmation, you have two ventilation holes where you see if your adhesive completely passed this gap for the adhesive to act. So maybe a more visual realistic application here, we build a transparent box just for really confirming to us how does this adhesive run through the channel. And you obviously use this is something which you can still play around with. So for example, if you increase the gap here, you can make the flow more easy for the adhesive. And here, for example, this was a cold cured adhesive. So it's a 2-component. It needs no additional heat basically to cure. And it was applied by hand. And here you can see it runs through the channel on both sides. And at first it fills this channel on the left or closer to us. And then after a few seconds, you see also that it's filling the second channel. Yes, and it's actually we took a more, I would say, harder case for us because it's a cold cured adhesive. It's mostly has a higher viscosity, so it's even more difficult to pump through. But even by hand, it's quite well possible to do that. So afterwards, we wanted to put our connection to the test. So we set up a crash test. In our case, the FOPS was the more critical load case. So we tested the FOPS and also simulated it. And for the ROPS, we took our validated model later to confirm the reliability of our design. So for the FOPS, we had this crash test with 250 kilograms of impactor mass dropping from a height of around 3 meters. And this is what you can see here in this video. This is a real-time video of the test. And you can see that the impactor mass hits the center of the tube, and you can see some deflection, but it's still limited. So the passenger would be safe in that case. Here in a more slowed down version, focusing more on the connection time, because that's what was the point of our interest. And you can see, obviously, you will have some sliding because of you need to go somewhere with this tube. The length is limited, but it's very well limited. So another important part for us was to show that we can also simulate this behavior, even this quite dynamic load case. So we set up a simulation with Radius, which is a explicit solver. We had the modeling of the tube, obviously, which is also very important. There we had a elastoplastic material with failure, because we also saw some failure of the tube on the connection part. The adhesive is modeled by a connector material. You will often see cohesive zone elements in that regard. So this is a, you could say, numerically very effective way to model adhesives. So these models still run quite fast, even though you often sometimes have these scaling difficulties with the adhesive. So the adhesive is quite small compared to the rest of the structure. And with these cohesive zone elements, or in that case, the connector material, you can have a quite coarse mesh and still be able to simulate the behavior of the adhesive. So that's what they're used for. This is how the model looks in the end. So on the left and right part, you have the nodes that are connected and are focused of our investigation. And here you can see the simulation of the impact. So you can also see some deflection in the middle, which is limited by the structure. Finally, the most interesting part is when you can compare your experiment to the simulation. And here again, the main focus is the deflection, which quite well fits the simulation. And also maybe as a background, we also support a lot of automotive customers there. These crash simulations are quite standard, you could say. And there, these cohesive zone elements or the simulation of adhesives is quite well, you could say, state of the art, and it works very good. So we're not very surprised that it worked good here as well. But yeah, still less than 10% off. That's always my rule of thumb, you could say, to be precise with my model. So finally, how do we envision this manufacturing process? You could take basically two paths, where you have a path where you have your sub-assembly with the adhesive bonding. So you take your nodes and connect them to your hollow structures. Or you could also at first go in the paint shops with your separate components as a second path. And then afterwards, obviously, you could also do the paint shop afterwards, after the joining of all components, or you could also use the already painted components and then finally join them together. And in the end, you would have your finished cap. So I think also very good to show how fast that works. We also set up a prototype where we tried out this concept of the mounting of the nodes and the hollow structures, and then joining them with the adhesive. So this is what you can see here in a sped up video. Overall, this is around 15 minutes of mounting time. So first you can see the bottom structure is pre-mounted and fixed. And then together with the vertical structures, in that case, the roof part is mounted. Everything is fixed, and then you apply the adhesive through the channels. First at the bottom part, and then at the roof part. and then you're basically finished. Depending on the adhesive, you would also need to consider obviously the curing time, and you would need to leave this cap fixed for that time until the adhesive cures, or you also just take spot welds and spot them at the connection parts in order to be able to remove the fixtures, for example. Could be two scenarios here. Yes, and finally, I think some of you already, or all of you already received the QR code. Everything that I showed you here and also additional information you can find in the documentation, which I think could be quite interesting for the engineers which want to maybe more know in depth how was the approach to the design or to design this node. And we also have additional information from our trials, for example, how to design one of these nodes, how to design the overall surface area that you would need, or what would be the gap then required for have proper adhesive flow through these nodes. Yes, and with that, I thank you very much for your attention, and I would give it back to you, Ron.
Wow, that was great. Thank you very much, guys. That was really, really good. Just a second here. Okay, so as Sergej mentioned, I did try to send the QR code to most of you, but some of your servers actually bounced it. I guess they don't like QR codes coming in. But if you take a picture of this screen or this QR code, it'll take you to the a registration page where you'll be approved to access the documents for this project. And yeah, this is I got to admit, it's not often that you see developments like this by a adhesive supplier done in a way that the results can be shared. Usually it's a collaborative project done with an OEM, and you can show pictures of the final thing, but you really can't get into the details of it because it's considered intellectual property. So that is great. So we're going to open it up for questions that the attendees may have. If you could use the Q&A feature within Teams, that would be great. And we'll open it up for questions. I got a couple off the hop here just to get us started. The first is temperature effect that you talked about earlier. Colder temperatures, I don't know if you've heard, but it gets kind of cold in Canada here.
I heard of it.
Is there a point you say where, okay, the adhesive, the strength is increased as temperature decreases? Is there a critical point where it starts to, the strength starts to degrade as you get into the -20s, -30s Celsius, -40s Celsius, or is it totally dependent on product?
So I think I would generalize for polymers if they see lower temperature and that the strength will increase. But the downside that you could have there is that you will have a more brittle product. So normally they have quite some energy, you could say, that the adhesives can dissipate until failure, and that could reduce if you have lower temperatures. But that being said, normally we can have a look and also onto the data, how the stress strain curve looks there, and you would see this if you would have substantially lower strains to failure. But in terms of strength, I think you could quite well generalize that you will see a higher strength with the lower temperatures.
Okay. It seems that we're having a trouble with the Q&A feature here that I need to turn something on. Just a second here. You know what we're gonna do here is if you have a question, just raise your hand, and I'm gonna let you into the meeting here. So if that works for you guys, my apologies. It's we're starting to use Teams. We were on Zoom, and there's obviously a few little things I need to learn. So. All right, I see Tyler, you've got a question. Just a second here. There you go, sir. Go ahead, Tyler.
Can you hear me?
Yeah, you bet.
Yes.
Okay. Yeah, I guess more like, well, initially just a comment. It seems like a big advantage could be eliminating weld pull from weldments and stuff, so that might be a nice advantage to this system. Just my question though is just wondering, is Sika looking to sell the nodes in the tubing, or do you just give kind of recommendations for dimensions of that interface?
We're not looking to sell nodes, we just sell adhesives, so we want to stick with that, what we know and what we can, but we can easily support you with the design of the adhesive node. So that's free to use, and that's why we also provide with the CAD data for you to use, and maybe as a starting point. And yeah, we can definitely support if you want to use this design and maybe adapt it to your needs. So yeah.
You know, the other thing that we could consider, Tyler, locally here, let's say that there's, pardon me, let's say that there's 2 or 3 companies locally that are interested in that kind of node design. What's to say that, you know, if we all agree on the size of tubing, and I know that would be really difficult to do, but to agree on the size of tubing that we're going to use, we could collaboratively develop the node, and have, you know, single orders out to a place that can cast them and that kind of thing. I know that it's a bit of a stretch, but you know, that we would all agree on the technical specs of this thing, but it is, I guess, a possibility.
Yeah, because I mean, it would definitely be good to try to have a more commonized node, because yeah, to machine them all would be pretty expensive. So to go to a casting would definitely make it more cost competitive.
Yeah, would agree. Would agree.
Yeah.
All right.
I was gonna just say, of course, this design, even though we did use a cab in this design, it could be used for anything like a truck body or things that do have a frame and have a meeting point there. So just to, as not everybody I'm sure on the call designs cabs, so just kind of keep that in mind that we can work with other designs as well too.
Yeah, and I guess another piece of this too is you know, how much money do we spend a year heating air for our air makeups for welding shops, right? And you know, if you can do this without having to heat a bunch of air, that's a cost savings right there, right? So okay, I've got a question here in regards to fatigue loading on these joints. Has Sika looked at, you know, obviously there's pull as you're trying to pull the tubes out of the node. There's the impacts, the ROPS, LOPS, that kind of thing. But as far as fatigue goes, I would assume that it would probably be superior to a weld joint because you don't have the heat affected zone. You've got large areas of adhesive in order to create the bond. Any thoughts on that?
So yes, as you said, it's in terms of fatigue, the adhesive joint will generally be superior. So normally what you aim for when substituting with a welded bond is to first verify that you, with your substitution, can withstand the static loads, and then normally it will easily sustain the fatigue loads. There is actually a quite interesting research project which was done in Germany, I think a few years ago, where they basically investigated this substituting welded joint with a bonded joint. And there, yeah, you could quite well see in the Wöhler line, so the fatigue performance, that you're always above with the adhesive joint. And for that, I mean, we also provide the data for that as well in our additional product information. So if you want to have a rule of thumb or just a guess how good it would act in your connection, you can also use that. So for this specific Advantage project, we did not look into the fatigue design, fatigue performance of this cap, because yeah, it's quite, I guess, expensive and to do a full, you know, big joint in the fatigue testing, but I'm very sure that you would outperform a welded joint.
Oh, and honestly, the majority of failures, I think that would be seen in heavy vehicle and equipment and steel steel structure design would be fatigue loading.
Mhm.
It's very rare that we would have a catastrophic load failure. It's usually always fatigue. Good. Any other questions out there? No, it doesn't look like it. So, oh, hold on, Tyler. Just turn you back on here. There you go, Tyler.
Yeah, just thinking more a little bit about what Curtis said. Kind of ideas beyond just cabs. I mean, I'd be curious. Parts can be painted before it. Yeah, I'm just thinking if you had a product where you need to break it down for shipping to maybe fit it on in a crate or something like that, would the Sika sell like potentially smaller, almost like one-use dispensers that maybe a dealer or something could just do some final assembly for putting the last little bit together or something like that? I don't know if that's clear.
For the cab, Sergej, do you know how much adhesive they used for that assembly?
I mean, you can see it in the video. I think it's just one. I don't know the English word for that, but it's
like one cartridge.
One cartridge, yeah. I think that's even less than one cartridge that you need for this kind of cap. So it's a very small amount actually of adhesive that you would need for producing this kind of cap.
Okay. So to answer your question, Tyler, it depends on the product. Most of ours are available in like 400 milliliter cartridges. The odd one is available in 50, but the majority are 400 ml.
Okay.
So in the construction video, they talked about obviously they need time for the adhesive to set up before you can move the cab. And it's going to be dependent on the product used. But
yeah,
just rough guess, how long would it have to sit in the jig before you could move it?
I mean, there are products where it's just a few minutes, and there are other products. In that case, we used a rather slow one because it was our prototype and we wanted to, figure out things a little bit. And there it's several hours. So it can really be between those. Yeah.
Okay. Is there a trade-off though if you use the faster adhesives that they're going to be harder and maybe less fatigue resistance kind of thing, or can you get the same properties between a slow and a fast adhesive? You just
no, not normally. So for example, if you have this one which we use, this is a Sika Power, this is an epoxy adhesive, and they normally take more time to cure. Of course, you can accelerate it a little bit if you have higher temperatures, and this one takes a few hours. Or you can, for example, use a acrylic, which are the more on the faster side, but they in generally have lower performances. So yeah.
Okay. Do you think you'd be able to pass a ROPS or LOPS?
Yes, definitely.
If you used the faster adhesive?
Yes, definitely.
Okay.
Yeah. It's in the end, it's a matter of the surface that you have then there, right? If you have a adhesive which has a lower strength, you obviously need a larger surface to connect these nodes. But most of the time also these acrylic adhesives have a lower viscosity, so we would be able also to fill a larger channel. So I could very well see this design also work within, for example, an acrylic adhesive which cures much faster.
Okay. I think Jason's figured something out here. If we use the chat feature, it actually works. The Q&A is still disabled. Will Sika be able to provide all technical engineering details around the adhesive properties necessary to incorporate into static and dynamic FEA analysis?
Yes. So you mean for this particular project or in general? So in general, you could say we don't have all of this data that we have, for example, for this product available, but for this project, we have quite a lot of data that we also provide. So yes, in general, we do. or we try to, if we don't have it, to get it. So I most of the time I have a big motivation to get it working for the engineers. So yeah, if we don't have it, we try to get it, or at least estimate it in some cases if it needs to be fast. So for example, testing takes quite some time, but since we have a big database and we know what some of the changes between the different adhesives are, we can also, if we don't have it quite well predicted or estimate rough, for you to have a preliminary design.
That's great. That's great. Any other questions out there? Just use the chat. And with that, I don't see anything else coming in. So I'd like to thank you guys for presenting to us today. On the screen, you've got the email addresses for Sergej and Curtis. So if you wish to reach out to them directly, you know how to contact them. The QR code that's there will get you to the technical documentation. After it hits a desk for approval, once you're approved, you can go in and get the technical documentation on this project. And again, I thank you for I thank you for presenting today, and wish you all a great Monday. Thank you very much.
Thank you for having us. Yes.
Yes, thanks for having us.
Oh, you're welcome. You're welcome. All right, everybody have a great day.
Bye-bye.